Assalamu alaikum warahmatullahi wabarakatuh. This is Dr. Ali El-Moursy in the microprocessor class. This is actually part 2 of lecture 27. So this is lecture 27 part 2. We are continuing with the slides for the floating point unit FPU, and we are in slide number 22. In the last lecture we finished describing the floating point status bits, and we will go to the next register to be explained here, which is the control register. It's a 16-bit register, and as you can see here, we can see different bits have different purpose and work. This register is responsible of configuring the machine. So actually the user can adjust the values of the bits here in order to configure the x87 machine to do some specific behavior. There are three main fields that we wanted to discuss in the control field here. Actually the RC, the PC, and the exception masks. Starting with the exception masks, the exception masks are bit per exception. We described the exceptions in the previous slides, discussing the status bits. So the status bits are updated whether there will be an exception happening or not. We already go over the different types of exceptions. The 6 exception: precision, underflow, overflow, zero, divide, denormalized operands, or invalid operations. Those same 6 exceptions have what we call the exception masks: precision, underflow, overflow, zero, denormalized, and invalid operation. So the purpose of configuring the exception masks here to indicate whether the programmer needs the exception to cause some routine to be executed or not. Like what? Like if you have an overflow, you want, for instance, you want to print some message to the end user that there is an overflow for the floating point or no. So it is the choice of the programmer to whether invoke some subroutine or some routine or some instructions when the exception happening. This is controlled by the mask bits. So if the mask bit, so if we here just describe, like we will describe one example here. So for instance, if I set the mask bit to 0, means if the precision fault happens, that means there is there will be no action will be taken by the processor. Okay. However, if I set the mask to 1, that means the subroutine for the precision يبقى execution of a subroutine. So if any of those masks have been set, if each of, hold a second. So if any of those masks have been reset to 0, that means no action. Means no action. Okay. If the mask is set to 1, that means this is an order for the microprocessor to execute. This is execution of some code. Okay. Definitely defined by the programmer in order to indicate what actually should be happen if this error happening. Okay. one of those 6 errors. Okay, so now the programmer or the user of the machine have the ability to, or the option to, either set those masks to 1 or 0 in order to allow or disallow the exceptions when they are happening, to invoke some code or not. Okay, we will discuss this in more details when we go to the interrupt chapter, inshallah, in lecture number 28. So as we have the 6 different exceptions, we will have 6 different flags for the masks, and as we mentioned in the last lecture, we have 6 different flags to indicate whether the exception is happening or not. This is the first field, so actually those are actually the first 6 bits here in the status or in the control register of the x87 machine. The second field that we want to discuss is the RC, which is called the rounding control. RC stands for rounding control. We mean by rounding control is actually controlled by 2 bits, and those 2 bits have, as we can see here, have 4 different values: 0 0, 1 0, 0 1, and 1 1. And these 2 bits indicate what kind of rounding to the numbers that needs to be performed for mathematical operations. Okay, so those are 4 different flavors for the rounding. I can round to the nearest, can rounding down or rounding up, or chop truncate to 0. Those are 4 different ways or 4 different methods for rounding the numbers for the mathematical operations performed in the floating point. The third field, which is maybe the most useful and the most important one, is the PC. PC here stands for the precision control. Stands for precision control. The precision control indicates what kind of IEEE standard or numbering system to be used here. As we mentioned, we are using floating point, and the floating point have different flavors. The single precision, which is 32 bits, the double precision, which is 64 bits, and the extended precision, which is 80 bits. So I can use the machine to perform the operation for, as we know, the registers are 80 bits, but I can, if I'm setting the machine to the single precision, that means I'm using only 32 bits of the 80 bits of the registers. Okay, or I can go to the double precision, 64 bits, or the 80 bits. Definitely the dilemma here is between the accuracy of the numbers and the calculation that I do, and on the other side, the speed of the computationals that I'm doing, and the memory that I'm reserving for the different parameters in my data segment. Okay, so this is actually what motivates me to go to between the smallest single precision or the extended. If I want a very high accuracy in my mathematics, so I will go for the 80 bits, low L extended precision, 80 bits. Okay, if I need a high accuracy, this is a high accuracy in mathematics. If I need a floating point with the reasonable accuracy, so I can use the single precision, which is using a 32 bits for the numbers. Okay, definitely here the accuracy, this is the lowest accuracy for the floating point that I can use. Okay, or in the, if I need the medium, I may use the 64 bit, and the mathematics for most of the application that we are using needs maybe 32 bits. If I'm doing a very advanced mathematics For some physics or scientific operations or chemical reactions, I may go to 64-bit. The 80 bits is definitely very high accuracy, and they may use it for very intensive and very precise numbers, because you have a lot of bits for the number and a huge range of values that can be represented in the extended precision. So as we can see here, this actually architecture or chart showing how the number of bits are being splitted between the fractional mantissa and the exponent in each of the three cases: the single precision for 32 bits, using 23 bits for the mantissa, fractional mantissa, which is actually aligned or normalized, and the exponent 8 bits and 1 bit for the sign. For the double precision, the fraction is using 52 bits for the fractional mantissa, the normalized, and the exponent using 10 bits and or 11 bits, and the sign is 1 bit. For the double extended, 80 bits are divided into 63 bits for the fractional mantissa and 17 bits for the exponent. To cover a little bit the instructions, this table is showing some flavor of the instructions for the floating point. We have floating point load, we have floating point store, we have floating point exchange, and floating point move. A lot of instructions are definitely in the floating point. However, the most important thing that we wanted to highlight here is definitely those instructions working with the single, double precision or extended precision. However, the most important thing that we need to discuss in more details is actually how these instructions are being executed. As we mentioned, we have a stack of registers, and these registers are accessed in a stack based or in the push and pop fashion, as we can see shortly in the following slide. However, before we go into the details of that, we want to highlight that also the instructions here are divided into a data transfer instruction, basic arithmetic, trigonometric instructions, and logarithmic instructions. So the instruction set for the x87 for the floating point is very rich with a very sophisticated and complicated mathematical instructions. The most important thing, as we mentioned, is to know how the instructions are working. Most of the instructions are involving two operations, either push or pop plus the mathematical operation. So as an example, the FLAD, the FLD, which is the load floating point, is an instruction that involves pushing data from the memory to the bank of register for the floating point. FStore, FSTP, is doing the opposite, which is popping. Those two instructions just doing the push and the pop. Okay, so those are kind of the equivalent of pushing and popping for the stack, but here this is the stack of the registers, as we will explain shortly in the next example. However, the other mathematical operations is doing mathematical operation in addition to the push and the pop. So to demonstrate how the machine is working, we will see in the next slide how things may be demonstrated. However, the slide here 29 is just showing a list of the different instructions that are being performed in the x87. As you can see here, all instructions start with the letter F to indicate that those are floating point instructions. So add, subtract, multiply, and or divide instructions operate in the following types of operations. So we can do the operation. The addressing modes can be either two data registers from the x87 register bank, or between the data register and the floating point integer value in, or floating point or integer value in the memory. The operands in the memory can be single precision, floating point, double precision, or word integer, or double word integer format. They are also can be converted to a double extended floating point automatically if this is needed. So this slide is very important, because actually this slide is showing how can simple code executed in the x87 machine. So assuming that I have those 4 values stored in the memory in labels in the data segment, value 1 storing the first number 5.6, value 2 storing 2.4, value 3 storing 3.8, value 4 storing 10.3. So assuming that already the data segment with those labels are storing those values, and I want to do the dot product in the designated equation here. So I want to multiply the first 2 numbers, multiply the second 2 numbers, and then add the 2 results together. So the code here is actually performing this operation with the stack of registers, as we can see here. The first instruction here, okay, is actually float. So this float instruction is actually what it's actually doing is that it push the data from the value, okay, from the value 1 into the top of the stack of registers in the TOS of the FPA, of the FR, or the floating point registers. So in this example here, maybe it is not shown, the ST0, the register ST0 was originally pointing here. So ST0 was pointing, yeah, ST0 originally is pointing here, that has the value of R5. Okay, after the first FP load, this the top of the stack, the ST0, is decremented by 1, pointing here, okay, and the value taking from value 1 of the data segment, and will be stored where? Into the first register here. So this is actually is similar to pushing the value from the memory into the stack register. Then second instruction, so after so this actually, this figure here, here shows a snapshot of the registers after executing the first instruction. This is part A. Okay, so we will show here in those parts the status of the registers after execution of each of my 5 instructions shown here. Okay, so basically now the second instruction here is fmul. Fmul is doing 3 things. It actually do this instruction is pop, okay, LST0, okay, and multiply it by the value at the memory location, okay, at value, okay, 2, okay, and then push the result back into the again into the location of LST0. So actually this instruction is popping, taking the value of 5.6, multiply it by value 2, the value 2, okay, here, and push it back into the same location. So after the second instruction here, which is instruction B, part B, I will see the following status of the register. At the same location here, ST0 at R4, I will have the result of multiplying 5.6 by the value 2, which is 2.4. The result will be 13.44 stored in R4, which is the top of the stack. Then I have another F load. the float is doing push. So this instruction will push into the stack the value 3.8. The value 3.8 will be stored or will be pushed into the stack. That means ST0 right now is being pushed one place to point at the 13 register R3, okay, and at R3 right now, after this instruction, I will have the value 3.8, okay. Then in the next instruction here, I will do another fmul. Fmul will do the same thing, will multiply this fmul, will actually multiply the value of 4 اللي هي 10.3. So the value 10.3 will be multiplied by the ST0, which is the value at 3 اللي هي value 3.8 will be multiplied together. This will be popped, multiplied by this, and then pushed back. So the result of multiplying 10.3 to 3.8, which is 39.14, will be at the end of part C here, will be stored at the top of the stack, which is ST0. Okay, يبقى at the end of ST of the C, I will have the result of multiplying 3.8 by 10.3 stored in the top of my stack here. Okay, the last instruction is the fadd, but here I'm doing fadd between ST1 and ST0. Okay, ST0 is this location, correct, and ST1 is this location. So fadd will add those two together. Okay, so that means it will pop the, so this instruction will actually do a pop for the 39.14, then add the value at ST1, which is 13.44, will be added together to give me the value 52.58, and will be pushed into the top of the stack, which is push at the top of the stack, which is still at the register R3. So this value will be stored here at the top of the stack اللي هو ST0, and this is ST1. Okay, so this demonstration shows you how the register is being used as a stack, and each instruction will either do just push or pop if it is load or store, or it is doing pop, perform operation, then push again. Okay, so this is the mechanism how the operation is being performed in the floating point machine. It's very important for you to understand how those instruction is doing, and you should be able to do a similar demonstration if this is being if you are being asked to do so in the exams or quizzes or whatever. So this is just a narration of the demonstration that we have just explained. As we mentioned, there are a very sophisticated instructions here: f sine, f cosine, f cotan, tan. So very difficult sophisticated instructions are logarithmic instructions, exponential instructions. Very sophisticated instructions exist in the x87 machine. And this is the last slide, and we have finished this set. We finished the floating point instructions, and the programs are not be covered in the theory, but you have to understand them. But there is no programming. I mean, it's covered, but there is no programming. If there is no programming problems for the floating point for the theory. However, this is not the case for the lab. In the lab, we will demonstrate. We have one lab to write programs, simple programs using float, store, p, and fmul, fadd, an example similar to what we have explained here will be exist in the lab with a full demonstration inshallah. Okay, and so this is the end of lecture number 27, part 2, and see you in lecture number 28, through which we will cover the interrupts chapter inshallah. Okay, thank you and see you soon.